This conference will now be recorded.
So, welcome again to those that are just arriving to our latest SCLF webinar. I'm delighted to have JP Renaud here today to speak to us on in-situ groundwater remediation. And I will just introduce them properly in a wee minute. Just to give you some advance notice, our next webinar will be, we're taking a couple of weeks off for the autumn break up here in Scotland. So the next webinar will be on the 29th of October. And that will be on groundwater monitoring by David Parks of SEPA, who I believe is on the call today. So we're very much looking forward to that. JP has, as you know, we always give our speakers the option of nominating a charity, and JP has nominated the charity Ronald McDonald House, who provide accommodation at and near hospitals for parents of sick children. So I'll be putting the link for that in the chat in a wee minute. So if you are able to make any donation to that, then it would be very much appreciated. So without further ado, I'm just going to introduce JP, who is Technical Director at ERS and a specialist contaminated land site investigation and remediation contractor. He started his career building hydrogeological models of contaminant fate and transport for the French nuclear industry, prior to a stint with SEPA's groundwater unit, providing scientific advice on groundwater abstraction, classification, landfills and contaminated land from a regulator's perspective. JP joined ERS in 2011 and his role includes overseeing the hydrogeological aspects of site investigations and remediation projects. So without further ado, I'll hand over to JP and look forward to hearing your presentation.
Thank you, and hello everyone. I hope you can hear me okay. Switch off the camera. So I was very delighted to have been invited by Alison to talk at SCLF. Alison initially asked me to provide a case study on an in-situ remediation project that ERS completed by the injection phase in July. But we thought it was too small in a way and too early to present that as a case study. But because the series of webinars on SCLF hadn't really touched remediation, apart maybe on the webinar on PFAS, I thought it would be a good idea to try to introduce a bit of remediation in the webinar series. And I suggested to Alison to try to put a talk where I would discuss a bit what steps a remediation contractor takes after the consultant has finished their risk assessment and essentially asks us to design on cost the remediation of the site. As a very brief introduction to ERS, we are the Scottish SME of about 30 engineers and scientists and geologists. We're a specialist contractor in contaminated land, and we do both the site investigation aspects and the remediation aspects. So we do have a site investigation division and a remediation division within the company. As I'm sure everybody knows here, contaminated land is a very broad church. I'm a hydrogeologist by training in a way. I decided to focus on in-situ remediation for this particular talk, but I'm not a chemist, I'm not a microbiologist, I'm a poor geologist probably. So what I'm going to describe today, by no means I would be an expert in all of those aspects of in-situ remediation, but I think it's quite common in contaminated land that you need, a team really to deliver a project. This isn't a user manual. I see this talk really as a quick walkthrough to show some of the steps that a contractor will consider when designing a remediation job. My understanding of SCLF is that the audience will largely consist of consultants and local authorities, SI contractors and some remediation contractors. I hope it's pitched at the right level, sorry. But by all means, do ask questions at the end if it was you know, if I went too quick or not quick enough on some aspects. So to go to the next slide. So what I'm going to try and cover today, a few minutes on what in-situ groundwater remediation is, what type of technique I'm going to be talking about. I thought it was worth having one slide about what a remediation contractor actually do, what we're actually being asked to do most of the time. And then really the walkthrough will start, and I've split it into 3 different phases. A phase about the mass of contaminant. I think in risk assessment we focus a lot on concentration, but for remediation it's mass which is more important. And then reagent selection and dosage, the distribution of the reagent in the ground, and then licensing. And it had to happen to me that I have a dog barking. I apologize for that. I'm going to sort it out. I'm so sorry, you'll have to cut that out of a recording, Alison. I don't know if you can do this. So let's start. So what is in-situ groundwater remediation? In my mind, it's all those techniques where we're going to either treat or immobilize the contaminants in situ, so without really moving it or taking it out of the ground. And really, I think that gives 4 key types of remediation. So chemical remediation, they're usually oxidation or reduction processes. We call them ISCO or ISCA, in-situ chemical oxidation, in-situ chemical reduction. Bioremediation, where we will rely on biological processes to actually consume the contaminant mass or transform it into something else. More recently, there's some work on immobilizing the contaminant. It's usually via sorption, via adding activated carbon into the formation. And there's also stabilization, where here we rely more on cementation type processes to stop the contaminant from actually leaching into the groundwater phase. There's a lot of other techniques which can be considered as in situ, and some of them are actually called in situ in their technical name. I would describe them as on-site methods because they have ex situ elements. So, for instance, pump and treat, there is the treating part is done ex situ, it's done at the surface. All the other extraction techniques, so soil or dual phase, multi-phase extraction. Surfactant and solvent flushing, again, usually that involves removing something at the surface. Air sparging and thermal desorption, again, usually that relies on some vapor recovery system, smoldering as well. So some of them are called in situ, in situ thermal remediation, for instance, is a common name. But I have little experience of these, and I see them as different from the 4 key ones that I introduced earlier, because there is an element of ex situ treatment in the process. With regards to in situ stabilization, that's not something I have much experience in at all. It's usually done by mixing directly in situ a reagent with the soil. It completely changes the soil matrix, and I've put on the slide a little pictogram that shows how that can be done with augers. So I will not cover that in my talk today. This is not something I've got experience of. I will focus on the first 3, and the first 3 really are usually done by injecting via direct push injection or injection wells. So to give an example of the type of injection that can be done, I've started with a direct push injection example. We usually at the end of the design end up with what we call an injection grid. So this is all those red dots that you can see on the screen there. On the right, the source zone has been delineated in purple on all those injection points need to take the reagent. And that's usually introduced in the subsurface using a specialist rig. In that particular case, we used a small rotary rig, which had a percussive head. It was a site in London. Often this is done with direct push rigs, geoprobes, which is a slightly different type of injection rig. But we don't drill a borehole in that case. We push a rod and we inject the reagent to treat formation. We can also deliver the reagent via injection wells. So I've got another example here, which is this project in 5 that I talked about earlier. On the right, you see the injection grid again. And on the left, you see just the top of all those injection wells that have been installed at each location. And here, the injection is done as a second step. So we come later on to add the reagent to those injection wells. I will show the design of them later on during the design phase of a webinar. One advantage of this method is that it's usually cheaper to put a second round of reagent into the wells because most of the time they can be kept during injection round. In terms of adding the reagent into the injection well, what you see on the screen is the type of setup that we used at that particular site. We have this big bar. I'm not sure you can see my mouse on your screen. This big bar on the left is actually connected to a packer, which seals the well near the injection zone. And then we have a pump that pushes the reagent through that pipe and then down into the well for injection. The blue instrument on the left is a pump that we use to inflate the packer so it gets stuck inside the well and seals the well for the injection. The last type of application of in-situ remediation is via permeable reactive barrier. And the example I've put on the screen here is a dry dock in Ireland, where what you have on the left of the screen within the blue area is actually a surface water feature. And the treatment was done via those 2 series of green wells that you can see on the left slide. So there are 2 barriers that intercept groundwater flow as it flows through and goes towards the dry dock. In that particular case, the treatment was actually consisting of releasing oxygen into the groundwater via something called oxygen release compound manufactured by Reagent that was pumped into the well. So it was a phase of polish of the groundwater after a longer phase of physical remediation at the site via pump and treat and bioremediation. So before starting into the steps that a remediation contractor takes when we're providing the data, I thought it was worth trying to summarize in just one slide what we're actually asked to do. Very often it starts a bit like this. We get an email telling us there's a report, somebody has done a site investigation, there's a pollutant linkage with groundwater. Could you give us a price for treating the groundwater? And really, when we get this, it starts a process where what we need to do as a remediation contractor is review the information that has been provided by the consultant or the client. And we need to understand the site, so the conceptual site model, what linkages require treating, require breaking, and also what the remediation objectives actually are, what the endpoint actually is. We then need to determine what the best way is to actually reach these remedial objectives. And as we do that, we're going to take a note of all the uncertainties along the way. So the things we don't really know or understand with the site. There may be things we haven't understood, or there may be things that haven't been looked at as part of the site investigation, but they may actually be quite important for the remedial design. And then we're going to put together a proposal and a price to actually do the remediation. On here, I say we need to price the job accordingly, because what's important to understand is that we will price in those uncertainties on unknown. So that may mean that for an injection job, we may need to allow for more than one round of injection because we're not quite sure at what concentration we're going to deal with. Or we may need to allow for further SI before we actually do the injection phase. So those uncertainties are actually really important when we come to pricing a remediation job. So I will now start with some of the concepts that we will walk through as remediation contractor when we start to consider the remediation of the site. And the first thing for those in-situ technique is we will need to estimate the mass of contaminant that requires treating. And there's a very simple formula to estimate that mass, and that's just the volume of groundwater requiring treatment times the concentration of that groundwater. But as we do that, we start to see that there will be decisions that we need to make. So to estimate the volume of groundwater, we need to have that delineated. And I will go through in a minute on how we will do that. So we need to delineate it spatially, laterally, at what end of the site is the contamination, how long is the plume, how wide is the plume, but also vertically, and often vertically is the more difficult thing to do. Especially when the number of boreholes during the site investigation was quite limited. Another important factor is that the groundwater doesn't fill, only fills the porosity or the effective porosity of the soil. So knowledge about porosity is actually very important in estimating the volume, and as you'll see later, it's something that actually not that well known very often, and we need to make assumptions on that, best assumptions. In terms of the concentration, we are going to need to find a concentration that's representative of a treatment thickness across the whole plume. We may, if there may be several plumes, we may need to separate them, but we need to make sure it's representative. And what's really important for us here is to know whether there is a source remaining, because if there is a source remaining on site, it's likely to be really difficult to treat by in-situ remediation, as I described earlier on. And often that source is NAPL. So when we treat organic contaminant, our first question when we look at the data is going to be, is there any NAPL in there? Where is it? What do we need to do about it? Often we would advise that it is removed before the in-situ remediation. So in terms of horizontal and vertical delineation, we will review the site investigation report, and we will generate concentration plots. We will generate groundwater flow contours, so groundwater level contours, calculate the hydraulic gradient, work out the groundwater flow direction, etc. Just so we can actually determine, how wide the plume may be or how large the area that we need to treat needs to be. Most of the time, we will do that by generating contour plots like you have on the top right-hand photo with right-hand chart with tetrachloroethylene and trichloroethylene at a former tannery site. Sometimes we use some different way of visualizing the data. I've got some bubble plot underneath where we can see in what boreholes we got the higher concentration just by the size of the bubbles, and the colors we present various depths of the wells that were installed. We will often generate cross-section in order to do the vertical delineation. And on those cross-section, we will put all the boreholes that have been provided to us and for which we have data. And we'll put both the geology on the screen. So hopefully this is visible on the slide. All those boreholes consist of two rectangles really. And we can see where the borehole is screened and what the geology is next to it. And this is quite important when we look at the concentration data, because it really shows us from what part of the formation the groundwater has flown. It's also quite important for sites where there may be NAPL, because we need to determine whether it may be that some NAPL has not been noted in a well because the screen is too deep. This is quite a time-consuming part of the data review. Electronic data, when it can be submitted to us, is fantastic here because we save a lot of time, and also the potential for error is really reduced. When we get issued a 500-page PDF file, it's very time-consuming to actually prepare the information in that way when it hasn't already been done by the consultant. So I would really encourage you, when you send data to your remediation contractor, to try to send it in Excel format or in AGS format for the borehole, so they can just import that very quickly into their software to work out, really the geometry of the problem. In terms of porosity, this is very, very rarely measured. There's actually very few reports that I remember reading where the porosity was actually measured. They're often on some very high profile chlorinated solvent sites in fractured bedrock. There are ways for us to estimate really what the effective porosity will be by describing the soil that have been encountered well. So really particle size distribution data, sorting coefficient, apparent density of the soils, if there have been some SPTs done, or sometimes some just description from the lead driller, are going to be useful to understand how compacted the formation is and what effective porosity may exist. But very often this will be taken from table of literature values, and we'll try to match that as best as possible to the information that's been provided to us in the report. Bedrock is difficult. It is much more difficult. I have put two photos of core boxes on the screen. This is a chlorinated solvent site in Aberdeenshire, and we have the same borehole on the return that we get. And I can't remember exactly the depth intervals, but we have a very, very long weathered sandstone conglomerate section, which probably acts more as granular material, but it is always difficult to know how much of the breaking up has been caused by the drilling itself, how disturbed the sample that we see here. And it's only much further down, but you can see on the right-hand side that we have more competent rock where the fractures are more likely to be the key determinant on the effective porosity. So during the drilling into rock, coring is really important if we want to estimate that porosity. And photographs of cores are useful when the core recovery is quantified for geotechnical purposes. This is very good as well, because we can use that to understand, the frequency of the fractures and their average size, etc. And that's something we will take into account when we estimate the porosity. In terms of determining a representative concentration, there's a number of things that can cause the concentration not to be that representative for remediation design. The first one is NAPL, and it's quite common that there has been a bit of sheen or NAPL noted, but the well was still sampled. And in that case, we can get some really high concentrations, which probably overestimate the impact of the organic contamination in the groundwater. That being said, that NAPL may need to be dealt with, but this is something to bear in mind. Long well screens are often a problem as well, especially when those well screens straddle different horizons. On the one hand, I guess it can make things better into inverted commas in a risk assessment purpose, because there is some dilution being done by the averaging process in a long well screen. But that may also mean that we assume a concentration of a very thick part of the aquifer, where in reality it is likely to be much thinner than this. We just do not have the data because the wave screens are too long. Another difficulty in establishing a representative concentration is when the wells are too far apart, and often during site investigation there are constraints as to where drilling rigs can be put and where it can be excavated. But obviously, as you've seen on the previous slide, when we do those contour plots of concentrations, there will be some smoothing being done and interpolation between the points. On really that can give us another estimation of groundwater impact when we're missing some wells in the middle. I think it's worth focusing on NAPL because NAPL has a huge effect on the mass. Effectively, if you have a site with organic contamination, some TPH or parts of TPH are the problem in the CSM, and there is NAPL, this is essentially a secondary source, which may be very difficult to deal with via chemical oxidation or bioremediation would be worse. Depending on the quantities, it's actually difficult to observe directly as well. So a sheen on the risings is relatively common during drilling, but it's hard to know sometimes because of the speed at which the drilling rig went, whether there is a significant NAPL horizon or if it is just a sheen. It's very difficult to quantify and establish that from drillers' logs. Interface probes can be quite difficult to use. I think if you look at the example on the right-hand side, the very small thickness of NAPL, it would be difficult to actually get that reading with an interface probe. If that NAPL was any thick, you may actually get a few centimeters rather than just a couple of millimeters that are here. It's also quite common on some solvent side that those probes don't function that well, and we have had issues with toluene at the previous site in London, where the same interface probe essentially stopped working after a few weeks monitoring at that site because the toluene itself damaged the probe. And this is an interface probe which is rated to be, solvent proof, etc. But we have those difficulties. What we would advise is if you get any hint of NAPL with an interface probe is to always put a bailer and actually see what is in the well. Now, what's in the well is pretty much always going to be another estimation of what is in the formation, but it is a good indication of what has been recovered. NAPL is not always easy to see in a bailer either. So the top right here we have, I think this one was, yes, I think that's actually a kerosene NAPL, a couple of centimeters in the bailer on the top right. I mean, it's actually very clear and not that different from the water underneath. We managed to identify it only because at the interface there is a bit of dirt there. Another reason where NAPL is sometimes difficult to identify is just because the screens don't allow the NAPL to flow into the well. So as I said earlier on, that's one of the first things we check when we try to establish whether we would expect NAPL in monitoring wells or not. So really often we will end up using the actual groundwater concentration as a proxy for the presence of NAPL. So I'm sure all of you are familiar with the well-known 10% or 1% rule. So 1% of solubility, you may have NAPL, a gradient of a well, 10%, it's quite likely. I don't think there are any hard rules about it. But what's important to remember here is that when we do those calculations, it is the actual effective solubility that needs to be taken into account. So that assumes a knowledge of the NAPL to start with. So when we have a NAPL mixture, let's say you're 50% toluene, 50% benzene, it's actually hard for the solubility of toluene that would have to be taken into account. And that's actually quite a low number when you look at it that way. So high groundwater concentration for us are likely to suggest that there is NAPL, and depending on the rest of the CSM, may actually suggest that that needs to be dealt with before an in-situ treatment. So if we have delineated the source of the plume laterally and vertically, gotten an idea of the porosity of the formation that we are to treat, and have estimated whether we have NAPL or not in the area we've been asked to consider, the next stage is really going to be deciding what reagent we are going to select and at what dose. In order to do that, it's really useful to know the environmental condition. So essentially the redox condition, the pH, M&A indicators. Are we seeing, for instance, that anaerobic conditions are being generated by degradation of hydrocarbons? And it's really useful to know this because we would want the in-situ remediation to actually build up on the current condition in the site. And it's not uncommon not to have that in the data that we receive. You know, M&A indicators, so your iron, manganese, nitrate, nitrite, etc., are not often, are not always monitored, but that's going to be quite important if we want to look at in-situ bioremediation, for instance. If we are going to consider bioremediation, the presence of microbes is really going to be quite an important factor. There are techniques that now allow us relatively quickly to know whether the relevant microbes are present that could degrade the type of contaminant. At the moment, I think it's mostly used for chlorinated solvents where there's some fairly well-developed assays and techniques using qPCR. qPCR is in the news all the time at the moment due to COVID, but similar tools are used to identify bacteria like Dihalococoides or Dihalobacter, which will degrade chlorinated solvents. And it's quite important to know the concentrations at the start of the in-situ injection job, because that will help us determine whether the population is large enough to degrade the contaminant, in which case a bit of biostimulation will be sufficient. So we may only need to make the environment more anaerobic by injecting some emulsified vegetable oil, for instance, or whether we may need to actually add a culture to bio-augment the site because we don't think that the relevant microbes are actually present. There is a school of thought that all those sites should be bio-augmented because it saves time, but there is a cost to all those things. And it's true that if there is evidence that the populations are already present, then biostimulation is likely to be sufficient. So we would like to see that type of data when it comes on our desk. And I think we start to see that more and more. And actually, we've invested at ERS so that we can do that type of testing ourselves now. But it's really useful as part of the design of in-situ bioremediation project. Oxidant demand is important. So essentially, organic matter, organic carbon. When we inject an oxidant, it's not going to focus on the one contaminant of concern, which fails the risk assessment. It's going to take the path of least resistance and oxidize what is the easiest to oxidize before it actually focuses on the contaminant, which is the problem in the risk assessment. So organic matter, organic carbon is an issue here because if there is a lot of it, we are going to need to require more oxidant. So it's important to have that data. The other one is co-contaminants. So there may well be contaminants in the groundwater which do not fail the risk assessment. So they are not contaminants of concern, but they're actually going to be very important in the design of the remediation because they will be the first one to spend the oxidants in a way. So we need to make sure that we degrade those before on leave enough oxidant for the next contaminants to be degraded. I have an example later on of a site where a co-contaminant is quite important. And when we have all this, so this is the data gathering stage really, well, we will consult reagent suppliers. So there's a number of reagent suppliers who manufactures oxidants, injectable substrate with zero-valent ion, emulsified vegetable oil. On those, their products have been optimized for various types of injection of soil mixings, etc. And there's a wealth of knowledge of what dosage, what would work, etc. So if we're able to provide them the mass, the groundwater flow, and the relevant concentration, they will then advise of what quantities of their oxidants would be required to meet the targets, which is required by the risk assessment. In some cases, we will do some bench testing beforehand. This is something we have started to do at ERS. We're using sodium persulfate. So there's just an example on the right where we developed a tool that allows us to detect what concentration of an activator has actually the best effect on the production of CO2 in samples impacted with diesel. The measuring CO2 is just a cheaper way to, in a way, determine how much of a contaminant has been oxidated, because it's a byproduct of the oxidation. So in terms of co-contaminants, it is very important not to focus just on the contaminants of concern that favor risk assessment. And I've decided to use this example here of a chlorinated solvent site to give an idea of what co-contaminants can do at a site. This is a chlorinated solvent site in Aberdeenshire. This one hasn't yet gone to remediation. It's at the characterization stage still. It's an industrial site that used a number of solvents, and you can see on the top right there is a tank farm with tank mark 16, 15, and 14 used to contain TCE. On the squares on the side are UST underground storage tanks, which contain a range of solvents, including toluene, MEK, and some mixtures as well, because there was a waste solvent recovery. And a number of leaks have happened through the past decades, and we end up in a situation where we have some very high concentration of chlorinated solvent in places, but they vary in terms of a distribution between the TCE, who was the parent solvent, and the daughter product. So I think it's probably quite hard to read, but if we focus on this table here, we have a borehole here, which is very close to the source, where the TCE is only a very small fraction of the chlorinated solvent in this area, 0.13%. So it's essentially gone. We have a fair amount of DCE, but most of what we can find is actually vinyl chloride. So there has been a significant amount of biodegradation in this area. But it has stalled at the vinyl chloride stage, because that spill is decades old, which is not uncommon. You need some really anaerobic condition to go past the vinyl chloride production stage. But we have other areas on site, so around borehole A11 here, and it's the same thing. If I try to zoom up to that little table, and I just hope you can see that on your screen, we have a much higher proportion of TCE. So here we have 86% TCE. It's a lower concentration. We're further from the source. It is just surprising to think that essentially the same we would have parts of the site where there's hardly been any degradation of apparent TCE, and some others where there has been a lot. And after a fair amount of characterization, what turned out at that site is that the reason for this was a co-contaminant. And I'm just trying to illustrate it here. There was a leak of toluene from one of those USTs that generated some very reducing condition in a plume, which I kind of I've illustrated with the ellipse here. And what we find is that within that ellipse, there has been a lot of degradation of TCE to daughter product due to the degradation of the toluene, which generated those anaerobic conditions. In other parts of the aquifer, so if we move sideways from slightly from that toluene, localized toluene impact, the aquifer is much more aerobic. The environment is not that good for the degradation of TCE, and then it seems that the TCE has been kept as TCE with a much smaller amount of degradation to daughter product than within the pink area in the middle. So that's what I wanted to cover in terms of the selection of the reagent and the dosage. The last part, really, we've estimated the mass, we've selected the reagent and the dosage, and we've engaged with our supply chain and made various, further testing here. We need to deliver that reagent. So the first thing will be to dilute it, and the reagent is always shipped in a concentrated manner to save on shipment costs. So we need to allocate an area of site as a batching area where we are going to be able to actually prepare it at the required concentration, the required volume, etc. And then it needs to be injected into the formation. And as I covered right at the start, there's really two key techniques for this. The first one is direct push, where we're going to push rods down to where we want the reagent injected. And there's various ways in which the reagent can be injected here, but a popular method, because it leads to less clogging in the rods, is what's shown on the screen here. It's called bottom-up injection. So we're going to reach the base of the area we want to treat, and then a volume of reagent will be injected, which gives you that blob at the bottom of the rod. And then we're going to pull the rods up to the next interval and then inject another volume of reagent and carry on up to the top of the treatment zone. So that's how direct push injection works. That can also be done top down. It's slightly more complicated in terms of the kit required to avoid clogging when doing it that way. Or it can be injected through injection wells. And really, I think injection wells are for bedrock, where direct push won't be applicable, or maybe for both sites where we know that a number of injection phases are going to be required. It may be that, for instance, the concentration are such that we know from the start that more than one round of injection will be required. So it may be advantageous to install some wells to lower the cost of a second round of injection. The example here is it's a well that was designed to inject into weathered basalt. And as you can see, it is essentially sealed with bentonite cement grout down to the weathered rock. And then we have a screen in the area that we want to treat. And the way we inject the reagent here is we put but I guess in a case like that, you could almost connect at the top of the pipe because there is only one interval. But if not, you would just lower down a packer, which is a small inflatable balloon with a lance going through it. And you inflate the balloon so it's located where you want the seal to be made, and then you inject through the lance, which will then provide the reagent through the slotted section of the well. When we do that, we need to control the pressure. It's very important. The first thing is we want to minimize daylighting. We lose the reagent, it comes to the surface, it's a health and safety risk. And also it doesn't go where it's meant to be if it's coming up to the surface. So daylighting happens when the reagent bypasses the formation. So it could, for instance, follow the outside of a rod and then come back up the hole. Or sometimes it just finds a preferential pathway and you end up seeing the reagent pop up in the neighboring injection well, for instance, if the two are connected by fractures. We also want to avoid fracturing of a formation. unless it's actually required as part of the design. We want to do that because if the formations start to fracture, and it's not designed that way, yeah, it's unlikely that the reagent will actually be delivered where we want it to be delivered. On the other hand, we do need the correct radius of influence, and we do need the correct volume to be delivered so that the treatment is satisfactory. So we want the pressure as low as possible to avoid daylighting and hydraulic fracturing, but not so low that we're actually leaving the reagent too close to the injection well. We would always advise to do a pilot trial for injection, because otherwise it's often very difficult to guesstimate from site investigation data what the radius of influence will be, and what pressure we would need to run the injection rig to actually achieve this. That testing can be done with clean water. In granular formation, it's relatively easy to design this. It's quite similar to the science of pumping tests and abstraction, except in reverse. It's much more complicated in complex geologies, especially there are some low permeability formations, or in fractured bedrock unless they've been very well characterized. So this is an area where pilot trials adds a lot of value. I wanted to finish with one slide on permitting. Doing in-situ remediation is actually a permitted activity because it includes an element of treatment of contamination. The licensing for this is country specific. It's controlled by the Environment Agency in England and Wales, SEPA in Scotland, and the NIA in Northern Ireland. The terminology is slightly different, the rules are slightly different. In Scotland, in order to do that type of activity, you need a contractor who has a mobile plant license, NAPL. And in order to actually do that type of work, they will need to write what we call the site-specific working plan. And this is a fairly detailed document that will explain all the steps that will be taken to achieve the in-situ remediation. So it will contain the methods, it will include the monitoring plan, which often will be similar to the verification monitoring stipulated by the consultant. It needs to cover all environmental controls that are required in order to deliver the project. So this is how all liquids, fuels will be controlled, dust, odor, vapor emissions, even mud, vermin, general waste, all this needs to be covered in the site-specific working plan. Protection of aquifers and other water bodies needs to be covered as well. So that document is essentially a very large risk assessment that shows that all those aspects have been addressed or assessed by the contractor and mitigation measures put in place so that the Environment Agency or SEPA is content that the works can go ahead. In order to hold a mobile plant license in Scotland, you also need a competent person who will be named on the site-specific working plan. So it's somebody with one-tap training, essentially. So that licensing applies to the treatment proper, but also for other parts of remediation jobs, which may be required and include treatment. So that could be trials and testing. So a pilot trial, for instance, of reagent on a small part of the site would require licensing under a mobile plant license in Scotland. For those injection projects where boreholes are required, so injection wells, and they are only drilled for the treatment, then the drilling phase needs to be done under the mobile plant license as well. And it's nothing to, in a way, the control that needs to be put in place are no different than what should happen on any drilling job, but it is just an extra layer of risk assessment to undertake, which sometimes could trip site drilling contractor when they haven't done that before. And this is, I think, my last slide, so I'm not sure how I did for length, but thank you very much. I hope you heard me okay, because I heard nothing for 45 minutes.
That was great. Thanks very much, JP. We are all still here, honest.
This was the most lonely moment of the past few weeks, I tell you.
Yes, yeah, it's quite a lonely experience. But thank you very much. It was a very interesting presentation. I'm just going to stop the recording now before we take some Q&A.